Okay, so this is problem 13-75. It's on page 581. It's a pretty simple problem. I'll read it from the beginning. A 180-pound man runs up a 30-foot high flight of stairs in 6 seconds. What is the average power developed by the man? And then part B, just notice there's a misprint there. It says 2 part A's. But in part B, if a 120-pound woman can develop 80% as much power, how long will it take her to run up the same flight of stairs? Okay? Sounds like we're back in grade school, boys versus girls. But anyway, here we go. So the man is 180 pounds, and we'd like to solve for his power output. Now this is just another symbol for power, W dot. We use it in thermo a lot, so I thought it'd be good to go ahead and use it in this problem as well. Trying to make sure everything will be on the screen. Looks like we're okay. I am going to switch colors though, because I don't know if blue will show up all that well. Let's go to black. So the power output of the man will just be force times velocity. Now, you might get a little confused with this. Remember in the book they've got this cosine of theta piece? And if you think about how the man is running upstairs, his velocity is really up the stairs, right? But the force that he's working against, or the force he has to apply to move upward, is like this, because it just has to be opposite of weight. So there is an angle between the two. Ultimately, what you find out, though, is what matters is the y component of the velocity. So the piece we really need is this, and that would be this piece. Does that make sense? That's really what we need, is just his y component of velocity. So, to calculate his power output, we'll simply take his weight, which is 180 pounds force. That's how much force would have to be applied to his body to get it to go up. Of course, it would be slightly higher than that to accelerate it. But once he's at steady state, you just have to keep 180 pounds upward on him. And then he runs up a vertical height of 30 feet in 6 seconds. Okay? So the units of power that we've got right now are foot-pounds force, or pounds force feet per second. Now that's not a unit of force that we're used to using, but do pounds force feet per second sound familiar to you? Is there a conversion factor you may have heard before? Should be like this. 1 horsepower is 550 of those pound force feet per second units. Both of these are units of power. Okay, it's just that we usually use horsepower instead. So let's find out how much horsepower output this man has. In fact, if you run the numbers, all you're going to do is take 180 pounds force times 30, divided by 550, and you'll find the man's actually generating 1.64 horsepower. Okay? So he's actually generating more than 1 horsepower. Is that possible? Yeah, it's possible. If you want to be a firefighter, there are certain standards that you have to meet. You have to be able to carry a certain amount of weight, a certain number of flights of stairs, and do things in a certain amount of time. The power output that a human being can achieve can be greater than a horsepower for a short period of time. But you can't do this continuously. In fact, the average horsepower for a human being is about a quarter horsepower or so. Yeah, that's what you could maintain for a decent amount of time. But if you're out of shape, you probably couldn't even do that. Okay, so it's possible, but he certainly wouldn't be able to run up, the Empire State Building like this. Okay, unless he's in really good shape. Now, what we know about the woman is that her power output is 80% the power output of the man. And I'm trying to use an M and a W. Hope it shows up okay on the video. So that's about 1.31 horsepower. If you take 1.64, 80% of it, it's about 1.31 horsepower. Now, the question is, how much time would it take her to run up the stairs? So let's work with the equation for just a minute. I'm doing this because I want to show you the relationship here. So power is force times velocity, but we could write that as force times change in elevation divided by however much time it takes to change that elevation. Now I'm using 2 symbols for power, and I'm using them interchangeably. One of them is W dot. The other one is P. Those are the same things. And I'll probably slip back into using W dot frequently. That's why I'm showing it to you now. Okay? But all we really need to do is solve for the amount of time required from this equation. And that would simply be the power output of the woman, okay, instead of writing P. Well, I'm sorry, I'm messing up. Let me try again. It'd be force times change in Y divided by the power output of the woman. Should be W not an M. All I did was I rearranged this equation to solve for time. So the woman weighs 120 pounds force. She also has to go up 30 feet of stairs, okay, changing her vertical distance by 30 feet. And her power output is 1.31 horsepower, which we now need to convert back. So 550 pounds force feet per second per 1 horsepower allows us to get rid of horsepower. Feet go away, pounds force go away, and you see that we end up with seconds. And so it only takes her 5 seconds when you plug this in your calculator. It took him 6 seconds. So his power to weight ratio is not as good as hers. I guess she's in a little better shape. I don't know. Okay? Does that make sense? Any questions?